the version of something like version of matter. Yes, we have some matter. Yes, we have different type of the matter and media and field. Again, electric field is the version of matter by means of which force influence on electric charges is carried out, which are taking place in this field. The characteristic of electric field, which is generated by biological structures, are the source of information on condition of an organism. Yes, we are talking again about the unit of the charge. It's a coulomb. Yes, 1 coulomb. It's a 1 ampere multiplying on the again ampere multiplying on the second. Yes, so we will talking about the again and again that our coulomb it's ampere multiplying on second, not dividing but multiplying. And this is the fourth characteristics of electric field is intensity vector. Yes, vector of electric field E or intensity E, it's equal to the ratio of force working in the given point of the field on a trial change to value of this change. Yes, so we are all the time we will divide our force of the field, which is working in the given point of the field, on the some special type of the charge, what we call a test charge. Yes, and we have variant of the some point charge, some special type of the charge which is have a sign. So we built this some graphically. We represent electrostatic field. It's with the help of some lines of intensity, force lines of intensity, the lines of the field. Yes, this is a lines tangent to which in each point coincide with the direction of the vector of electrical vector E or intensity vector E. Yes, intensity is the vector which direction coincides with the direction of the force working in the given point of the field. It depends on positive point charge or positive dot charge, we could call it. Its dimension is the E. It's the Newton per coulomb. Yes, or it historically named it's volt per meter. Yes, it was made historically from this division of the electricity science. Yes, so graphically we will represent our field with the help of the lines of intensity or force lines. All the point, each point of this lines tangent with the coincide of the direction of vector E. Yes, of the direction of the vector of intensity. And here is that we have the figure of the lines of on the figure A and B of the figure 1. We have these two point charges are shown. Yes, a positive and respectively negative charges. Yes. And on figure 2 we have the lines of intensity for the system of positive and negative charge on the sum distance between them. Here is the electric dipole. Yes, here is our dipole. And intensity of the field of a dot charge in vacuum in a scalar form It will be determined under the formula that your intensity vector is equal to charge Q for model of that divided on 4πr squared multiplying on epsilon 0. Yes, so this formula, it's explain us what is the relation between the intensity of the field of the point charge or dot charge in vacuum to the direct distance from the point when we measure it. Yes, so the distance in the denominator and the power of 2. So if the distance between 2 point charges are twice it, their intensity will be lower in 4 times. Yes, so because we have the r squared in the denominator. Power characteristic of electric field is the potential U or potential phi, another Greek letter. Yes, in practice often we used concept of potential difference between points 1 and 2. That is known as electric voltage. On the figure 4 we have the electric voltage. It's a difference between two potentials of points of dot charges or point charges, or potentials difference between 2 points of the field. It's an electric voltage. Phi1 minus Phi2. This is your U voltage. The potential difference of 2 points in the field is equal to the ratio of the work of the forces of the field, and it's a moving on dot positive charge from one point of a field to another. Yes, to value of this charge. So we are this difference of potential P1 minus P2 will be equal to the this ratio of the work of the forces of the field on a moving positive charge from one point to of a field. Yes, to the value. Yes, so we move for the positive charge from one point to another point, and we divide it to the value of this charge when what is the move. Yes, so these forces of the moving of the dot of the point, a positive charge. Yes, so potential of given point of the field is equal to work which is made with the forces of the field at moving of the unit positive charge from the given point to infinity. Yes, so or the end point where the potential of the field is accepted equal to 0. We will think that every potential of the given point. Я занята, у меня пара. Рот закрыла и закрыла дверь. А где Таня? Господи, ну я занята, ну. Potential of the field, here is the story, it's the family. Yes, or the point where the potential of the field is accepted equal to 0. The potential in any point of the field in vacuum for the dot charge is determined under the formula phi is equal to plus minus q divided on 4p epsilon 0 divided on r. Yes, whereas the sign plus concerned to the case of positive charge and sign minus to the case of negative charge. Unit of potential is called volt. So we would measure potential or potential difference or our voltage. Yes, the difference of potential of the 2 points of the field it's volt. 1 volt it's 1 joule per 1 coulomb. Again, the surface for which all points have the identical potential, it's called equipotential. Here is a dotted line on the figure 5 and figure 2. The force lines and equipotential surfaces are mutually perpendicular. Between potential and intensity, it's in the given point of the field, there is dependence. Yes, there is dependence between the potential and intensity of the field, or the vector, normal vector of the field is the derivative of the potential. E is equals to d phi on the dl. Yes, so it's the derivative of the change of the potential in this space here. It highly depends on the distance, how it's distributed in space. Yeah, where is your differential phi? Yes, the phi is a change of potential. Differential the phi is a phi2 minus phi1. dl, it's a small displacement from the given point along the line of intensity. So we will introduce our distribution and dependence, potential and intensity of the given point of the field, like the derivative of the potential of the electric field through the space. Yes, so something like the small displacement from the given point along a line of intensity. Sign minus here in this formula number 4, it's caused by that intensity of the field is directed aside decrease of potential. So because the potential, yes, always decreasing in the reverse side, whereas the intensity. So for homogeneous field, change of potential on unit of length of line of intensity, yes, or line of intensity along the line of intensity, it's called potential gradient, and is defined by as grad phi. So gradient phi here, because there is a derivative from distribution in space. Yes, how we change in space. What is the distribution of our potential? Potential gradient is the vector directed aside for the greatest increase of potential, always. Yes, directed aside the greatest increase of potential. The vector of intensity and the vectors of potential gradient, they are equals in each point of the field on magnitude and are guided to opposite directions. So the vector of intensity of electric field is equals to minus gradient of the potential but the potential of this field, of minus potential gradient. Yes, so the electric dipole, we are going to our explanation of electrocardiogram, and we need to talking about the electric dipole. Dipole in electric field, what is that? Electric dipole is a simple system consisting from equal point charges or dot charges opposite in sign, here on the figure 6, which centers are on distance L between them. We could call it shoulder or arm. Yes, the main characteristics of the dipole is dipole moment. P is equals to Q multiplying on L. It's equal to product of value of the charge, our Q, because they're the same in the model but different in the sign, opposite in sign, and they have the distance between them. We will call it arm. Yes, arm of the dipole. Unit of the moment of a dipole is coulomb, meter. Coulomb multiplying on meter. Yes, P is equal Q multiplying on L. Q is in coulomb, L is in meter. Dipole moment is the vector directed from the negative charge to a positive charge. Always, yes. He was made historically. Dipoles are polar molecules of proteins, for example. If the centers of positive and negative charges are on some distance L, yes, on the figure here, 7, and dipoles could be molecules of amino acids and also water here under this figure 8. Yes, H plus 2H plus with the angle between these two arms nearly 105 degrees of the angles, yeah, and the O minus, the oxygen minus here. So the hydrogen, 2 hydrogen and 1 oxygen. The other substances are included in tissues of organisms. So we have different type of the dipoles. Are some molecules of amino acids and also water, and also many different substances included in tissues of organism. In complex albuminous molecules, each connection can have the dipole moment. Yes, therefore the dipole moment Pm of the complex molecule will be equal to the sum of dipole and the moments of separate connections. P dipole moment is equal to the sum. Yes, this mathematical sign for the different summarization of the dipoles moments on the separate connections P1 plus P2 plus P3 till Pn. So we turn it to the sum from I equals 1 to n. Yes, Pi. This is the explanation how to make this sign easier. Yes, at placing of a dipole in a constant electric field of intensity E, yes, on the figure 9 here, when the dipole will operate pair of the forces here. The one of the force F plus Q multiplying on E, yes, will turn up this dipole to the left, to the right hand, and the minus will it's minus F, it's equal to minus Q multiplying on E. So they are aspiring to establish dipole along the field, something like turning up this dipole towards the same direction of the field. This phenomenon of orientation of dipoles in electric field has received the name of polarization. Exactly this means, yes, this is the polarization actually. The moment of pair of forces will be equal. Yes, because apparently it will be equal. You could see it in the picture here because we have the same sign, the same Q, yes, the same charge and the same vector E on this field. That's why this moment of pair forces will be equal to M equals to Q multiplying on E multiplying on the L here, yes, and the sinus alpha. What is the alpha? It's the angle between your F, yes, and your P vector. So in vector form, your M moment of pair forces will be the M vector equals to the this multiplication product of two vectors. Vector P, yes, the dipole moment multiplying on the vector of the electrical force, yes, normal electrical force intensity. If dipoles to place in the variable electric field, they could be turned, yes, they will turn about the position of the balance in the step to change of the field. So on such turns of dipoles, some energy or capacity of variable electric field will be spent, so which will be allocated as a heat inside the medium consisting of dipoles. So this heat is the it's placed, its basement is on the turnings of dipoles. Some energy or capacity of variable electric field which is spent to the turning of dipole, yes, which is be allocated as the heat inside the medium consisting of dipoles. The dipole molecules of the tissues of organisms also make turns in alternating electric field with allocation some heat. Yes, it's always allocation some heat. This phenomenon was found application as a physiotherapy by field or UHF. Yes, the hearing frequency, yes, ultra special frequency physiotherapy of the field is some ultra high frequency. The electric field of a dipole, we need talking about that. A dipole represents systems of two opposite charges and creates electric field in a medium surrounded. We shall find expression for intensity and potential of this field in the beginning on axis of the dipole and then in any point of the space around of the dipole. It is necessary for us to find value of intensity in the point A on the axis of the dipole here on the figure 10. As your L is small enough, your the distance between two discharges much more less than the your distance to the point of the field, or you could say that the distance from the point of the field much more bigger than the arm of the dipole. Yes, so your R will be much more bigger than L. Yes, and hence your R plus will be equal to R minus to the R. So the field in the point A will be created by charges Q plus and Q minus. Therefore, we can write this the intensity of the field or normal vector of the field EA in the point A. On the axis of the dipole, we will find the value of intensity of the point A here. So it will be the sum of the intensity of the plus charge and plus intensity of the charge with the minus sign. Yes, so we could fill up this formula with the previous formula. Yes, when explain our E again. Yes, here is our E vector and it's a gradient here, and your again, and we will fill this formula with the explanation what does it mean. Yes, and don't forget that we have actually the same not actually the same distance between these two charges. Actually, we can write the first inside these two brackets. We will write that we are divided the amount of the charge Q plus, the first charge plus divided on r plus distance to the point, yes, squared. Don't forget that it's squared always, because the r squared, the distance in the power of 2 in the denominator when we're talking about field, yes, and minus q minus, yes, the charge of the minus dot divided on r minus squared, yes, and we multiplying these to these distances, because we are needed to explain what we happen here, and we will make the same denominator to work with these two ratios, yes. And don't forget that when we have the same denominator, we are multiplying numerator of two ratios, yes. That's why we have the r in the power of 4 in the denominator, and we have this special type of the two brackets in the numerator. So we have q, k is some constant depending from the choice of the system, yes, there's some constant of proportionality here, but don't forget that we have two brackets here, r minus plus r plus, multiplying on r minus minus r plus, yes, and sum of this distance will be r, yes, some of them will be L, yes. So we will have in the result we will have K2Q RL product divided on r in the power of 4. We could cancel it 1r and r power from this ratio when we receive the K2P, yes, the dipole model divided on r in the power of 3, yes. And you could write the vector of intensity of the electric field. We could write it like EA equals to 2p divided on 4p epsilon 0 on r in the power of 3 in the system of International System Unit C. So for value of potential of the field, we shall receive an expression that you have your U, or difference of potentials of the field, equals to the vector of intensity of the field multiplying on r, on distance from the point, yes, from the dipole. It will be equals to 2p divided on 4p epsilon 0 r squared, where it's your epsilon 0, it will be 8.85 multiplying on 10 in the power of minus 12 farad per meter. It's your some electric constant of the vacuum, yes. So we need to make some necessary explanation for us to find the potential in the point A, remove it from the charges accordingly on the distance r plus and r minus on the figure 11 here. So in this case, again more more closed. In this case, as well as intensity, the potential is created by both charges, and it can be found under the formula UA in the point A, yes, will be KQ multiplying on these brackets, whereas the denominator will be 1 and denominator will be R plus minus L divided on R minus. Yes, so we also could make it by the previous formula. Yes, we turn up to the our L, our arm, yes, between the 2 points to the R, to the distance from the points of the felt. So it will be R Q K multiplying on this ratio R minus R plus, dividing on R plus product to R minus. Yes, so when we have your K, don't forget that your K, the constant, is dependent on the choice of the system, and when you put inside this model that assumption that we have R plus much more bigger than L, R minus much more bigger than L, it means that the distance from the point of the felt, we can choose that it's much more farther than the arm of the dipole. Yes, so the difference between them you could show us that the difference between this R minus and R plus will be like L multiplying on cosine alpha. Yes, there, this what is the alpha? It's your angle between your R and the vector of the arm of the dipole. So in psi international system C, you could imagine that potential is created by both charges, could be found under the formula UA equals to P, the potential of dipole, multiplying on cosine alpha, divided on 4p epsilon 0 R squared. Don't forget that R squared is in denominator. So when we're using this formula, it is possible to find the potential difference of two equidistant points A and B, whereas the K is your constant dependent from the choice of the system, will give you the difference of potential or potential difference of two equidistant points. Here is the QA minus UB equals to P divided on 4P epsilon 0 R squared, multiplying on cosine alpha minus cosine alpha B. Yes, so we under the formula 7 again, we could find that potential in any point of the medium surrounding the dipole, and under the formula 8 here we shall find the potential difference in 2 points. It is necessary to know that the human heart also represents the dipole created in a space surrounding its electric field, and accordingly some potential difference. So the concept of dipole electric generator or the current dipole. The equivalent electric generator is the model physical system, or some model. Yes, almost in all existing physical models, the electrical activity of bodies and tissues reduced to the certain set of current electric generators, which are taking place in the volumetric conducting medium. The equivalent circuit of the current generator in the conducting medium is submitted on the figure 12 here. In this circuit, E is your EMF of the source, so electromagnetic field of the source. The resistors here are big. Yes, big. R is equivalent to resistance of the conducting medium. Resistance R little, it's internal resistance of the current generator. Resistance R little many times over exceeds resistance R of the conducting medium. So the R little much more bigger than R big. Yes, under the law of the Ohm or the ohmic law, yes, the current equals to I0 in the system. What is the I and I0 of the force of the current in the generator? Yes, and the total current of the medium. So the I is the force current in the generator, and the I0 total current in the medium. And this will be equals to the this vector of intensity on the circuit. E is your EMF of the source. Yes, some special type of the electro moving forces of the source. Yes, electromoving forces of the source, and your this is your numerator, and denominator will be the sum of these resistances, two resistances. Resistors R, it's your equivalent resistance of the conducting medium, and the resistance R little, it is internal resistance of the current generator here. And don't forget that this R little is in many times over exceeds resistance R of the conducting medium. Yes, but if you have this R little much more bigger than L, you could rewrite this law of the Ohm of this circuit like I equals to I0. Yes, the force of the current in the generator and the total current of the media will be equal, and they will be equal to the electromoving forces of the source divided on this resistance R little, internal resistance of the current generator. Yes, we could make this transformation because the resistance R many times over exceeds resistance R big of conducting medium. Yes, from the last formula it is possible to draw the conclusion: the force of current in the medium will remain constant since the current does not depend from the resistance of the medium. Yes, so in this circuit resulted on the figure 11, terminals K and K2 here, K and K2 here. Yes, the source of voltage in the possible to present as a dipole. So in other words, the equivalent electric generator is current electric dipole, or the system consisting of positive pole. This is the positive pole is the source of electric current or outflow, and the negative pole inflow, the located on the small distance from each other. So the spatial structure of electric field created by such generator in the medium is defined by position of its poles. Yes, so the current dipole is not pure abstraction actually. It is possible to make its actual physical analog. For example, if we join two wires to cell, for example, battery or generator, and we need to sink wires ends to the saline solution, or the some solution of the special type of the salts or the solids, something like acids or something like that. In a bath, if in a bath with the solution to sink the two electrodes to which we can join the voltmeter. For example, this special device which is measuring the volts here, the indications of the voltmeter will equal to the potential difference between these 2 points. So we have the difference of potentials of 2 points of the field where these electrodes are dropped. So the main parameter of the current here, electric dipole, is the current dipole moment or dipolar moment. D is equal to this vector dipole. It's equal to this I vector multiplying on L, which is the vector variable. Yes, in resulted formula, I is the current on dipole equal to the total current in the medium. L is the distance between the poles. Yes, the direction of the vector of dipole moment is accepted from the negative pole to positive. It's coincide with the direction of the current inside a dipole. Yes, and the human heart here on the figure 14, human heart is possible to assimilate to a current dipole. A current I0 inside dipole heart flows from the minus to plus and the medium from the plus to minus. Yes, the current I0 is equal to the total current proceeding through the medium surrounding a dipole. In the hard dipole, the negative pole will be area of a muscle, where there is an excitation. This is area is sinoauricular node. Sinoauricular node again. Yes, figure 14. A current dipole is the charging dipole creates in the conducting medium electric field. Lines of intensity of the electric field is of charging dipole are identical with the lines of intensity of the electric field or the current dipole, so they coincide with the lines of the current. Yes, don't forget about that. And we could talking about that dipoles depending on their size and chart. We have they differentiated them on 2 types. We will call that we have dot and finite dipoles. Dot is called a dipole or point dipole, which occupies infinitesimal volume of the space. With your arm of the dipole, it's going fast to 0 again. And the potential of the field of a finite current dipole in the point A can be expressed by the formula similar to the formula 7. If in last Q here, don't forget that your P, the dipole, your dipole will be equals to product of the amount of the charge Q on the arm of the dipole. So to replace on this, we need to replace our Q, our charge, to the I, yes, to the our current in dipole. Yes, here is that. I it's a current in dipole, so it's something like equal to the total current in the medium, and L is distance between the two poles. Yes, this when we turn up to this formula again, we need to replace our product of the dielectric properties of the vacuum of the and the electric property of the media, the spatial constant and features of the media, how they transfer and product the distribution of electric field vector, on the 1 divided on rho, this special ratio of reversed rho, another Greek letter. Yes, so UA, so your difference of potential or voltage in the point of A will be this special type of the formula, D multiplying on rho divided on 4πr squared multiplying on cosine alpha IA in the point A. Yes, so don't forget that your alpha here is the angle between the direction of registration of potential and the direction of the vector of dipole moment D. Yes, the potential difference between 2 points A and B in that case will be this UA will be equals UA minus UB. Yes, the potential difference, or the difference of potential between 2 points N and B will be D multiplying on rho divided on 4πr squared in the denominator and multiplying on these brackets where is inside the cosine of alpha of point A minus cosine alpha point B. Yes, from this formulas, the previous formulas and this, we follow that as well as for charging dipole, the potential difference from the current dipole is directly proportional to the dipole moment D and inversely proportional to the distance squared or square of distance from the negative pole to all the dipole. Yes, so the square of distance is always standing in the denominator, so it's inversely proportional to the square of the distance from the negative pole or the dipole in this particular case. Such potential differences created by a hot dipole are projected on surface of the skin of the person. Remove it with the help of electrodes and exactly register it with the help of electrocardiograph. So again, we are going exactly to electrocardiography, the physical basis of electrocardiography actually. So all living cells of human tissues and plants could be, and they are, sources of electric potentials which have received the name of bioelectric potentials or biopotentials. The registration of biopotential of tissues and bodies with the diagnostic or research purpose has received the name of electrocardiography here. Yes, so electrocardiography or electrocardiogram, like on figure 15, ECG, ECG, yes, in the Russian ECG, yes, in the actually in the American system we have it ECG. Its registration of the biopotentials arising in the cardiac muscles and its excitation. Yes, and we have different type of this ECG or AMG or the EEG variants of the different type of the registration of biopotential arising in the muscle of excitation. Electrocardiography, ECG here on the first one. Yes, so we have the registration of biopotential arising in the cardiac muscles and its excitation. Electromyography, AMG. Yes, it's a method of registration of bioelectrical activity of the muscles. AMG is used for diagnostic of diseases or clearing up of physiological state of the muscles. It allows to find out the pathogeny, the mechanism of development of disease, how it works, yes, and also to inspect productivity of therapy. At AMG here in the figure 16 we have this special type, the result of registration dependence of the difference of potentials or your voltage in millikilovolt to the dependence of the time in seconds here. At AMG, electrons are of small square are superimposed in the relevant points along nervous trunk of a muscle. In the norm, the arbitrary traction is accompanied by the expressed myogram of frequency in 100 Hz and more, and amplitude up to 2000 millikilovolt. Microvolt, it's better, yes, microvolt. So micro, don't forget that micro is a 10 in the power of -6. On the figure 16 here again we could show in an electromyogram, yes, the common extensor of the fingers. Yes, electromyography here, it's something like registration of bioelectrical activity of the spatial type of the muscles, common extensor of the fingers of dextral hand, slow rhythm of inflection, extension, something like that. When we moving your finger, slowing rhythm of the extension and ligation, inflection, extension. Electroencephalography, EEG. Figure 17, it's a registration of bioelectric activity of the brain. Yes, we also have this special type of the bioelectrical activity of the brain. Electroencephalogram is a curve reflecting integrated activity of the large number of pyramidal neurons of a cortex of the cerebrum and propagation of waves of excitation on nerves. So we have first one, we have this integrated activity of a large number of special type, we'll call it pyramidal neurons of the cortex of cerebrum, and then we have propagation of the waves of excitations on neurons. The rest potential of pyramidal cells here, it's from 15, yes, -50 up to -80 millivolt, 10 in the power of -3 volt. And the amplitude of the action potential is the 60 till 100 millivolt. At duration of the in time, it's 0.52 millisecond. 10 in the power of -3. Yes, don't forget about that. And for feeling of oscillation of electrical potential in the time, electrodes are superimposed in various points yes, of integument of the head, or immediately during the surgical operation. So we have variance of this distribution of electrode. It could be superimposed in various points of integument of the head, or it could be immediately moving during surgical operation on a particular departments of the brain. Number of electrodes depending on the purpose, it's varied from 2 up to several tens of them, numbers of electrodes, yes. So electroencephalograms here on this graph difference look like the composite oscillations with various frequencies. Here on the picture is 18 from 1 frequency from 1 till 100 Hz, and they have different amplitudes as in time dependence and from position of electrodes on the surface of the head. Yes, we have different frequency here and the time dependence, and don't forget that we always have a calibration of the signal. We need to make a calibration, so we put on the graph always the lengths, yes, the length of these electroencephalograms. So the reference of the distance on the graph is 1 second. Here it's a horizontal line, 1 second durance here, yes. And to another type of calibration, it's your vertical line of 0.1 millivolt. From plus to minus. You can give us a calibration to frequency here in a millivolt, voltage difference between 2 points of the dipole. So for examination, this electrical activity of the brain at various functional states coincide a prime sign wave oscillations on which, under the theorem of Fourier, yes, it's possible to analyze the composite oscillation electroencephalogram. Yes, again we have this electroencephalogram here, and we turn it EMG, it's electromyography. Yes, here we put the electromyography, EMG. And don't forget that when we have an oscillation, some prime sine wave oscillations, we can use some special type of mathematical theorems which give us the possibility to analyze some composite complicated oscillations and share them and react with them, how to they summarizate or minuses with the spatial type mathematical theory, a theorem Fourier, give us a possibility to consider some prime sine wave oscillation to analyze this composite oscillation of electromyography. So we have some mathematical physical apparatus to work with such type of the oscillations and to analyze them. So at wake person dominates a special type of the rhythm of the work, the regime, the work of the brain. We will call it alpha rhythm. A rhythm, it's something like a type of working brain system. The oscillations is of this our electroencephalogram. It's over frequency of 8 till 13 Hz. It is observed also beta rhythm. with a frequency of 14 to 35 Hz, gamma rhythm from 35 till 70 Hz, and delta rhythm from 0.5 till 3 Hz, theta rhythm from 4 till 7 Hz. So we have different type of the rhythms of the brain working, types of the work of the brain of our organisms. But in the wake person dominates alpha rhythm, the oscillation over frequency of 8 till 13 Hz. Yes, on the occurrence or vanishing of particular rhythm of the brain, yes, on the could be reflected on encephalogram. It is possible to judge the character of the functional state of the brain and to estimate different pathologies of the brain, of working brain. Yes, the basic rhythms are more or less exhibited at epilepsy, tumors of cortex of cerebrums, or different another change brackets of the basic rhythms show us the different pathologies. So estimate these pathologies. And we go into electroretinography, ERG. It's the registration of biopotential of retina of an eye. Here, it is used as additional method of a diagnostic at diseases of retina. After impulse elimination of retina filling of potentials, it's yielded through the electrode solder in contact lens, which superimposed approximately. Then yield transient flashout of patent flashlight valve. Yes, to comparison various aspects of electrography on amplitude of signals in millivolt. Yes, don't forget, a milli is a 10 in the power of -3. Yes, volt, and on frequency band in Hertz, it's shown here on the table. So we have the different type of parameters of electrocardiogram, electroencephalogram, electromyography, and electroretinography, and we have a different amplitude here. Yes, millivolts. Yes, so they are working electroencephalogram and electromyography are working and the one starting amplitude, but they have the differ in the ends of this range of the amplitude in millivolts, and we have different range of the frequencies in Hertz here. Yes. In most cases, the biopotentials are removed by electrodes, not directly from the body, a heart or the brain, and from other next tissues, in which electric fields are created by these bodies. So we need to stop in more detail on physical basis of electrocardiogram. The physical approach of electrocardiogram consists in creation or the choice of special type of model of electric generator, which the bestly corresponds to the picture of removing potentials. It is experimentally established that each cell which is possible to assimilate to a current dipole as at excitation generates action potential. In the excited myocardium always there are many dipoles. We shall name this elementary. Yes, elementary. We shall note that dipole potential of any one elementary dipole is proportional to di. To the I multiplying on the cosine alpha. Don't forget about that. So we have special type of the dipoles. Yes, di, it's a dipole vector. The model of this is dipole vector d. It's, in other words, this is a projection of vector of the dipole model, yes, on a straight line. So always we're talking about the vector dipole moment, but at this time we will talking about the di multiplying on cosine alpha I. Yes, it will be the projection of the vector of the dipole moment on a straight line, which is connecting beginning of the dipole and the point of measurement of potential. Yes, so this meaning of the this potential, the this potential U of the electric field of the heart will be depends from the rho multiplying on this dipole moment di, this multiplying on the cosine alpha I. So it depends on this the amount of the projection of the vector of dipole moment on the straight line, which is connecting beginning of the dipole and the point of the measurements of potential. And this potential U of the electric field of the heart develops from the dipole potentials of the elementary dipoles. So we something like summarize them. Yes, very tiny elementary dipoles. We summarize all these dipoles and give us the result of this potential of electric field of the heart. As during each moment of cardiac cycle, rather small site of a myocardium is reset. Distance from all dipoles up to the point of measurements of the potential are approximately equal to each other, and you, yes, your potential of the heart, yes, again, potential of electric field of the heart can be described by this expression that UI will be equal to rho divided on 4πr squared in the denominator, multiplying on this sum from I equals to from 1 to n, di multiplying on cosine alpha I. Yes, where is your r here in the denominator squared is identical to all dipoles distance up to the point of measurements of potential, and your n, so we summarize to your di from 1 to plus 2 plus 3 till the n, till the all the number, final number of dipoles. So proceeding from the specified representations, a human heart, it is possible to consider as a multipole generator dipole. Yes, something like multipole generator, multiple dipole dividing total action potential. In this formula here, 12, yes, we are sum of projections of this dipole moments can be considered as a projection of vector of the dipole model d0, yes, on the one current dipole, for which will be d0 vector will be equal to the sum from I from 1 to n, whereas the n is the all number, final number of the dipoles. You are you have many big sum of many multiples. Yes, many small particles poles, and you have the final big sum of this multiple generator dipole, giving us the total action potential. This dipole here will be called equivalent dipole of the heart. So again, this this sum of projections of the can be considered as a projection of the vector of dipole moment d0 of one current dipole, for which we have this sum of di from I to 1 to n. The n is the total number of dipoles, and this dipole is called equivalent dipole of the heart. Thus, the potential of external electric field of the heart can be presented as a dipole potential of one equivalent dipole. So your difference of potential or potential of external electric field of the heart can be presented as this dipole potential of one equivalent dipole, rho multiplying on d0, or multiplying on cosine alpha, whereas the alpha it's the angle between d0, yes, dipole moment, vector of dipole moment projections of one current dipole, yes, whereas your d0 will be the sum of your di from 1 to n. Yes, and the d0 is the model of vector d0. Yes, model in which the electric activity of myocardium is replaced by action of one point equivalent current dipole, and potentials of external field could be described by this expression 12 and 13. They will call it the dipole equivalent electric generator of the heart, or the integral electric vector of the heart pH. Yes, integral electric vector of the heart pH, or d0, or the dipole equivalent electric generator of the heart. The validity of the equation 13 provides to be true that potentials measured on the surface of the body during the fixed moment of the cardiac cycle are approximately directly proportional to cosine alpha and inversely proportional to the distance. Don't forget that we have power of 2, yes, distance squared. So in other words, the physical approach to the electrocardiogram consists in a choice or a creation of the model of the electric generator, which corresponds to the picture of potentials removed from the surface of the body. Yes. So we build the model which gives us the possibility, which gives us the real physical model or approach to electrocardiogram, which give us a possibility to create a model of electric generator which corresponds to the image of potentials removed from the surface of the body, because we need to find the dipole equivalent electric generator of the heart, or integral electric vector of the heart. And we are going slowly to the theory of leads of Eindhoven. Theory of leads of Eindhoven highly uses the word the vector electrocardiography. Yes, it is experimentally established that heart dipole during excitation generates action potentials, which on the surface of a human skin gives the lines of equal potential, equivalent lines, something like that. On the figure 20, the position of the dipole moment of the current dipole of the heart and equipotential line will be shown. Yes, if through a heart dipole to lead, yes, the straight line AB, and through the center of arm or dipole perpendicular 0, 0, Then on the part of positive pole of the dipole heart settle down positive, and on the part of negative negative lines of identical potentials. Yes, we have this equipotential lines here, yes, like equipotential surfaces here, yes, with the special type of the difference of the heart potentials. We have some zero line of zero potential, which actually have zero potential. That's why it receives that name, that label. And it's something like mirror of the symmetry, yes, from the different equipotential surfaces which are lying dispersed in a space near the heart, near our heart system. And from drawing the visible, and that if to apply an electrodes on various points of the surface of the body of the human, of the person, yes, it is possible to determine the potential difference delta U of all these points. For the first time, theoretically proved points on the surface of a human body from which it is possible to take a potentials of the heart have been offered by Einthoven. As a dipole representation about heart underlines the theory of leads of Einthoven. Yes, Einthoven is a Dutch scientist, father of electrocardiography. So we need to talking about the main postulations of Einthoven theory. They are: the first one, the electric field of the heart is represented as electric field of the current dipole, pH, yes, vector, which is called the integral electric vector of the heart. Yes, and second postulation, pH, the integral electric vector of the heart, is in homogeneous isotropic conducting media, that is tissues of organisms. And the third postulation, the integral electric vector of the heart permanently changes its direction and volume. Its beginning is in the auriculoventricular node and may be considered as its constant position the end of the vector for the one cycle of the heart work makes this compound special curve, and its projections of the frontal plane forms three loops which are marked as P, Q, R, C, and T on the figure 22 and 23. On the surface of thorax, Einthoven has determined 3 points, A, B, and C. Yes, again, A, B, and C. They have 3 points of the show us this our integral vector of the heart. Yes. It's a spatial type points on the surface of the human body, which is possible to take a potentials of the heart have been offered by our Einthoven. Again, yes, so we are going more about this surface of the thorax of the Einthoven. We have determined the 3 points A, B, C. To having connection there, it is possible to receive equipotential triangle, triangle of Einthoven, in which center there is a dipole heart generating action potentials. Yes, we have this dipole heart in the center, so generation our electrical potentials of the heart inside this triangle points. Yes, equipotential triangle, again, triangle of Eindhoven. In center is a dipole heart generation action potentials. The potential difference between any tops of triangle, which will be directly proportional to the projections of the moment of current dipole on any of sides of the triangle. Yes, your change of potentials delta U1 is your delta DAB. Delta U second DAC, delta U third DBC, or the difference between ratio between this U1, U2 and U3 equals to this ratio between the this poles, yes, these dipoles P1, P2 and P3, yes. So this difference of potentials, yes. Don't forget that we have integral electric vector of the heart. So we have 3 integral electric vector of the heart here, and we have the ratios of the potential difference between these points or any tops of triangle. They are directly proportionally to these projections of the current dipole, moment of the current dipole of any sides of the triangles, yes, or the integral dipole of the heart, P1, P2 and P3. And taking off the electrocardiogram, electrodes settle down in as points which can be counted electrically equivalent to points ABC of Eindhoven triangle. Eindhoven has suggested to place electrode not in tops ABC and on right arm RA, right arm, left arm LA, and left leg LL. Yes, on the terminology of physiologists, the difference of biopotentials registered between these 2 points of a body, it's known as a lead. Yes, here we have this triangle here on the scheme of the human body triangle. Yes, right arm, left arm and left leg. Yes, and exactly between them we have 1 potential, 2nd potential and 3 potential. This difference of biopotentials registered between 2 points of a body, it's known as a lead. So we have 3 leads here: right arm triangle point, left arm triangle point and left leg triangle point. We need to distinguish the first lead, right arm, left arm, second lead, left leg, right arm, left leg, and the third lead, it's your left arm, left leg. Yes, so they are corresponding to potential differences delta U1, delta U2 and delta U3. As the electric moment of current dipole heart changes in time in leads, will be received the time dependencies of voltage, the potential difference. That is called exactly the electrocardiogram on the figure 22. Yes, we have this exact line, yes, dependence from the millivolt to the time in second. Yes, we have this cardiogram give us the string of the paper with the line on it, the cardiogram. Yes, dependence of time, dependence of voltage or the potential difference. two maximal values of potential in various time interval of reduction of the heart had been given names P, Q, R, S, T, waves of electrocardiogram. On the figure 22, it shows the normal human electrogram. Yes, electrocardiogram here, it's normal human electrocardiogram, and the pathology of the form of these waves, their size is changed, that will allow to use electrocardiogram for the purposes of diagnostic. Feature of electrocardiogram. The P wave occurs during the depolarization of the atria, which causes atrial contraction. Yes, the QRC, QRS wave corresponds to depolarization and subsequent contractions. Yes, subsequent construction of the ventricles on figure 26. The T wave occurs during the ventricular repolarization, which corresponds to the relaxation. Yes, we have this hand here with the QRS symbol, and we have this special type of the heart working, like we have the P plus polarization, repolarization, and these four acts of the heart working system. Yes, this scheme of recording of the QRS wave of the electrocardiogram in 3 standard leads shown on the figure 25 here. Yes. The signs plus and minus corresponds to a signs on the axis of the electrocardiogram in the corresponding leads. Electrocardiogram does not give representation about the spatial arrangements. I will make it a little bit lower. Yes, so we not have the representation about the spatial arrangements of the vector D0. However, for the diagnostic purpose, such information is very important in this connection of the method of the spatial research of electric field of the heart, name it vector electrocardiography, is applied here. Yes, and little bit lower again. So the vector electrocardiogram here flat on the figure 24. We have electrocardiogram here flat. Its geometrical place of the point corresponds to the end, I'm gonna make it lower again, to the end of the vector D0, which is exactly, господи, да что ж такое? Which is exactly shows the possibility to how heart is working. On the projections to any plane change of position of D0, it's possible to write down the with the help of electronic beam. On the screen of the cathode ray oscilloscope of vertocardioscope are observed separate loops P, complex Q, R, S, and T, which has give the doctor, yes, the more information at setting of diagnosis on the wave of electrocardiogram. Yes, these projections of the vector cardiogram on the plane can be received by addition of voltages of 2 mutually perpendicular leads here. Yes, on this picture. So we have special type of the figure 23, have special type of the 4 acts of the heart working system. Yes, when we have the received on the vector cardiogram, the plane can be received by these 2 spatial variants of the leads. Yes, we have 3 leads, and some of them could be summed inside this triangle. Yes, so we have addition of voltages of these 2 mutually perpendicularly leads here. And at many illnesses of the heart, the form of flat here vector cardiogram is sharply transformed, and it is used in the diagnostic purpose. So for example, loop QRC here, yes, the different projections of the loop of the QRC give us the projection to the horizontal plane. There is no bottom part at heart attack or some sides of the heart. Yes, you could find in the internet. Actually, I'm not a specialist, I'm just give you how it works. Yes, so but I actually know, when I collect in this material, I actually know that many explanations how the electrocardiogram is working, what is the different type of the heart problems, projections of these QRS problems on the horizontal plane. There is no bottom part at the heart attack or some sides of the heart. So initial inflating pulse originated in sinus node, rhythm maker cells, and propagates to the dextral auricula. Yes, and a little bit bigger. Yes, the after activation of auricula here, yes, we have something like rhythm sinus node or rhythm maker node, rhythm maker cells, and we have propagations of the pulse through the dextral auricula. After activation of the auricula's impulse propagates on the conductive system of the heart to the atrial conducting system, to the ventricular conducting system, bundle of his bundle branches, yes, Purniger fibers, yes, Purnicia fibers. I'm not very familiar how to pronounce it right. Purniger, I think, Purniger. And it attains to a myocardium of ventricles, which is spread of activation from endocardium to epicardium on the figure 26 here. Yes, and the next will be different type of the cardiac current, and we today we are up. Yes, the time is absolutely up, and we are finished it today. Yes, that's why we need to stop this type of the variants of our lectures, and we need to talk in about